In this video, we're going to take a look at finding the distance between two lines, specifically the distance between two parallel lines. So on your notes, you have a lot of words for instructions, but I kind of want to boil it down a little bit um, and just sort of try to condense things a little bit. So whenever we're looking at this, our first step is going to be to graph these two lines. So we're going to start there. These are both in slope-intercept form. So we want to just start by plotting our y-intercept and then using our slope. So I'm going to put kind of as many points as I can on here. First, to help me draw a straight line because I can't use a ruler on my tablet. And second, because we're actually going to be using these points in a moment. So that's my first line. And let's get my second line. So remember, these are supposed to be parallel lines. So if you graph them and they don't look parallel, just double check how you graphed them because something probably went wrong. Okay, now we want to find the distance between these two lines. So the shortest distance between two parallel lines is going to be with a line that is perpendicular to both of them. So since they're parallel, if it's perpendicular to one, it's perpendicular to the other one. So what I'm going to do is start with sketching a line that is perpendicular. And I'm just going to start with the upper line. And I want this perpendicular line to go through a point on that line, a point that I know, an integer point. So I'm going to pick the y-intercept here. All right, and this, we're not going to really be using this for anything other than a visual, so just sketch it as best as you can. Okay, so I'm going to put a little 90-degree marker there since this is my first, my perpendicular line. Okay, so I'm going to note this intersection point. So this is the point 0, 4. All right, now on here, this right here is going to be our distance. That's our distance between the two lines. So what we need is a second point because our distance formula uses 2 points. So we have to find this second point down here. It looks like it might intersect somewhere nice, but it probably doesn't. So what we have to do is write the equation of this perpendicular line. And I'm going to write it in slope-intercept form because that's the easiest. So our perpendicular line in slope-intercept form. So that's y equals, we need an m times x, and then we need a b. So the way that I drew this line, it was already using the same intersection y-intercept as that red line. So it's still going to be plus 4. That's still the y-intercept of that blue perpendicular line. And then for my slope, because it's perpendicular, it should have an opposite reciprocal slope to that original red line, that first red line. So it's the red line slope is 1/2. So the opposite reciprocal of that would be -2. So there's my perpendicular lines equation. Okay, so now I want to solve for this second intersection. So I have my first intersection up here, and I want to solve for my second intersection. Well, the easiest way we have to find an intersection of two lines is by solving a system of equations. So when we have two linear equations, if we solve their system, then we're essentially solving for that intersection. So this is going to be reaching back into algebra a little bit. So my two lines are y equals -2x plus 4. So that's my perpendicular line. And now we're working with the second line. So y equals 1/2 x minus 3. So we want to solve this system to find the intersection. The easiest way to do that is going to be substitution. If they were both in standard form, we would use elimination, but then since they're both in slope-intercept, we're going to use substitution. So I'm simply going to take this second bit right here, says, okay, that's y equals, and I'm going to substitute it up in here for that y. So we're going to say, all right, well, 1/2 x minus 3 needs to equal 2x plus 4. And actually, this should be a -2x plus 4. There we go. Okay, so we're going to go ahead and solve this for x. So we're going to add 2x to both sides. We're going to go ahead and just make sure we're leaving everything as fractions while we're working through this. We just want to be very careful about not rounding in the middle of our problem because it's going to create quite a large rounding error at the end if we do. So let's see, we should have 5 halves x minus 3 equals 4. Okay, adding 3 to both sides, we'll get 5 halves x equals 7. And then we'll go ahead and multiply both sides by that reciprocal. So we'll take 7 times 2/5, and we'll get that x equals 14/5. Okay, now we're just going to simply use that in order to find y, because we need a second point. We have part of it, 14/5, but we need a y value for a coordinate point as well. So we're just going to substitute it right in. Doesn't matter which equation you substitute it into, just pick which one looks better to you. So I'm going to take the first one, so y equals -2 times 14/5 plus 4. So go ahead and do that in your calculator or in your head, whichever you prefer. And you'll end up with y equals -8/5. All right, and then it's always just good to double check, does that make sense as your point? So we're expecting this point to be in quadrant 4, where x is positive and y is negative. Yep, it's in quadrant 4. It looks to be in the approximately correct location. So that's all good. So it's just a quick double check. It's not foolproof, but it can certainly help if we had any errors there. Okay, so now that we have that, we can go ahead and find our distance. So we're simply going to plug very carefully into the distance formula our 2 points that we found. So first point, second point, and then we're going to find our distance. So our distance is going to equal the square root of, and it doesn't matter which direction we do this difference in, it's because we're squaring it, so we're going to get something positive. So 0 minus 14/5 squared plus 4 minus -8/5 squared. Go ahead and type that in your calculator and we'll grab a distance. And at this point, because we're at the very end, we can round to the nearest hundredths for our answer. All right, and we should find that our distance is approximately, and we'll use squiggly lines to indicate approximation, 6.26. All right, and that is our final answer. All right, we're going to do one more example. I'll go through a little bit quicker now that we've kind of written down these instructions and gone through it real closely. Okay, so first step, draw the lines. Okay, so we're going to draw, or graph would be a better word to use. Okay, so we're going to graph the lines. 2, 3, 4, 5, 6. Okay, so this one doesn't quite fit on here real nice, so we're just going to do it real approximate here. And then we have a slope of 4. All right. Okay, so because this graph is only helping us visualize, having a real accurate graph isn't super critical. So don't worry too much, except it does help if I graph that sort of correctly here. 2, 3, 4. There we go, that's better. All right, now we can connect those. Okay, so even though we had one being a little bit off kilter there, off the graph, that's okay. We're just trying to give ourselves an approximation of what this is going to look like. All right. Okay, so we got these graphed here. Okay. Now we don't have a great intercept to use, but we do have one down there at the very bottom of our y-axis on this, the visible portion of our coordinate plane here. So we're going to use that. It's always nice to use a y-intercept because then it makes writing our perpendicular equation very easy. So we're going to sketch and write the perpendicular. Okay, so we're using this as our initial point for our perpendicular line. I know it looks like it goes through that other line, but it doesn't necessarily. But we're definitely going to use this as our first point. So our first point is going to be this 0, -6, and our perpendicular line is going to be y equals, and we're looking for that opposite reciprocal slope, so -1/4 x, and then the y-intercept -6. So that's our perpendicular line. Okay, now we need to solve for second point. So this is where we're going to use our other line, the one that we didn't just use the intercept for, and solve that system. So we're looking at our perpendicular line and our second original line. Okay, so those are the two lines, and we're going to solve this system. So easiest way to solve this, since they're both in slope-intercept, is going to be using substitution. So I'm going to kind of just set those right-hand sides equal to each other. So -1/4 x minus 6 equals 4x plus 7. So this would be a great moment to pause the video, try this yourself, and then we'll come back together and see if we got the same thing. So go ahead, pause, try to find your x. All right, so we should have gotten that x equals -52/17. So again, just leave it as a fraction. All right, -52/17. Is it kind of an unusual fraction that we don't work with frequently? Yeah, but don't worry about it. We have a calculator. So now we want to substitute that back in to get our second point. So y equals 4 times -52/17 plus 7. And again, it's a weird fraction, but that's all right. We got a calculator. All right, and we end up with -89/17. Okay, now we have 2 points. So we have that point and our first point, which we used, which was an intersection. Now we just want to plug it into the distance formula. So our distance is going to equal the square root of 0 plus 52/17. So I'm doing addition because it was subtracting a negative there. Then that squared plus -6 plus 89/17. Again, subtracting a negative, so I just wrote it as addition. All right, and we're just going to throw that all into our calculator, and this is the time where we get to round. We're going to round to the nearest hundredth, and our distance is approximately 3.15.